So yesterday I was just tinkering around with an idea of whether a neural network can decode a particular like maybe encryption scheme, and so I just implemented a very simple scheme first. I implemented the Caesar cipher, which basically just shifts like maybe in this case the alphabets by like three or by a certain amount of shift. Okay, so this is like the shifted message, and then we can generate like maybe a 10 digits worth or 10 letters worth of message, and then we could do like a certain a way to convert this to numbers and then do a one hot encoding into a neural network. Then we can see that the network contains like just from the input layer is 10 letters with 26 characters, and then we can have like a flattened layer to flatten all of them so that I can do another dense layer, which is like a fully connected layer of 1024 nodes. Then this will go into 10 separate outputs, which will output the respective letters accordingly. So this model kind of works. I mean, it isn't that surprising because a Caesar cipher is a one-to-one cipher. Like if you have an A, it will always be mapped to an A. If you have a B, it will always be sorry. If an A always mapped to a D, a B will always be mapped to an E, a C will always be mapped to an F, and so on. Yeah, but if you watch my previous video, you realize that I had some issues with the output array. Yeah, so for those who are doing like multiple outputs, make sure that your input to the model, like this train output here, is also in the form of an array, a multiple output array like this. So I actually had to spend some time to do this. Initially, I had some issues because the training size didn't match. So that was for what was done yesterday. So maybe today we could up the difficulty. You can see that actually learned pretty well. It learned to like get the output really fast. Okay, it'll be different if we had actually like all these letters as a total group identity instead of splitting into characters. We do it as like A B C D as one character. That will be different because then that will be 26 to the power of 4 possibilities that we could possibly have, and that will mean that it is harder for the network to actually learn anything. So that is the thing right now. Okay, so after that we can actually do a quick test. We can test whether the network learned anything, and indeed, you see, if we just change the string a bit, like maybe a Z, you can see that yes, GHIJK and Z will be mapped to F and so on. So it actually learns the kind of mapping. Okay, so now, okay, what we can do next? Okay, we can actually make the network. Okay, try to like okay, there are a few things that could be done, but maybe the first thing that could be done is okay. Right now, we actually hard code this shift. Can I do this shift? Like, can it learn the shift? So, dynamic shift between 0 to 26 will be fed as an input to the network as well. So, instead of just having a network like this, my shift variable s over here can also be fed into the network itself. So, can the network learn based on this shift? Let us see. Okay, I mean, I don't have to change anything here. Okay, the only thing that I need to change is my inputs here. Okay, we do have to have another input here. Input 2, and the shape will be 1. Okay, so in this input 2, this will represent the amount of shift is a number value. This represents a shift variable. Okay, so now what I want to do is I want to actually put in my shift variable somewhere in the network so that it can actually like affect my network itself. So one way to do this is to just like after I do a flatten layer here, we could also have this shift mm, I could have it as a separate input actually. I could have it as a separate input. So like we could do this like so we can have a concatenate. we can concatenate the inputs. We can concatenate x and input 2. I mean, because it's in the same dimension, it's like been flattened already. So this should work. Yeah. So the inputs here will then be, there's like input 1 and input 2. Yeah, so we have two different inputs now. Okay, cannot be obtained with flattened layer. Okay, let's see what's wrong. Oh, because I put inputs. Okay, so now we have two inputs. One is to represent the shift. So if this network learns, okay, with that particular shift that I inputted, it should shift my letters according to the Caesar cipher accordingly. So it is sort of like learning the Caesar cipher. If it works, okay. So previously I've tested out. If I don't have this shift here, I fixed the shift as like a certain number here. Okay, the network may not a network has no issues learning. So now let me just do a quick check. If I just put my shift as 6 permanently, I feed in this shift to the network. Can the network learn? Okay, so first up, we have to do some shift in the input that we calibrate to the model. This train input itself, okay, needs to have the shift encoded to the train input. So let us do that now. So my inputs here, my input process over here will need to, yeah, basically it will need to have the shift encoded in as well. So let's see, maybe I could have it as a separate input. Yeah, I think it's easier to do it as a separate input. So something like this, train input with s, like that. Yeah, has input with s, where s is the shift. So yeah, we can just add the shift in. So now the shift is still fixed. It is shift of a 6. Unable to find handler to handle. Okay, okay, let's just search Keras how to uh, enable multiple inputs to model. Okay, so if we want to do a multiple input model, how do we do the train function? So if we have two inputs like that, yeah, so we have two inputs like this, model inputs will be like that. So that is correct. I mean, we did. And then how do we train it? Okay, let's see. Yeah, I'm just looking for their train loop here just to see how they did it. So if we do have two inputs that we want to train the neural network is, uh, okay, actually this doesn't look like it's the same data set, isn't it? It is for images, or image plus numeric and concatenate. Exactly, I did that, so that's fine. Okay, model, okay, this one, all right. Okay, so yeah, I'm just interested in the model dot train. So okay, model dot compile, model dot feed x equals to this. Yeah. Okay, I think I know why. Okay, because in this case, my s over here needs to, maybe I should put another thing here. Like this is for the concatenation. Okay, so maybe this is for the shift variable. So what I need to do is, my shift here is 6, right? Okay, maybe I do this later. I will just hard code this in right now, like shift times 50,000, shift times 10,000, and then shift times 10, because in this case the shift is fixed. Okay, so it looks like we need to sort of do this with a fixed number, right? Like maybe 6. Will this work? Okay, let's just All right, let's just do it the hard way. Let's just create. We just call it train input shift, val input shift, and test input shift equals to in this case s. Okay, let's just see what's the train input shift. How does it look like? Okay, then maybe we should convert into a tensor. Convert this to tensor. Yeah. So let's convert this to a tensor. You can convert to tensor. So like this. Okay, so this is a shape of 50,000. Okay, great. Let us see whether this kind of works. So train input shift, file input shift, test input shift. Alright, seems to work. Okay, so now we have encoded the shift variable inside the network itself, and then we just need to see whether or not the shift parameter can be sort of learned by the model. And it looks like it's learning something. Okay, because in this case my shift is constant, I think the model can actually choose to ignore it, which I'm pretty sure it did. Yeah. If we look at the weights for the shift, later we can just take a look at the weights for the shift layer. Like maybe dense 202. Yeah, yeah, maybe at the first dense layer you can see like the last weight which should correspond to the, yeah, you can see the weights for the last layer later. Okay, so then now we can do the model like that, and then we can put in our shift over here. Okay, just give it a while to run. Okay, so okay, somehow this, oh, I put it inside here. Yeah, let's just do this reshape thing, and then I need to come up with my new variable like that. Okay, let's take a look at this. The model contains this first part. Okay, and then it contains the second part here, which should be the shift that we want it to do. Let's put this shift value like that. Okay, so the model itself could work already if we do it something like this, like test input shift. Let's take a look at the tensor of shape 10,000. So if we do like a tf dot convert to tensor, what will we get? We get a tensor of shape nothing. Okay, which is not good because we do want a shift of 1. Okay, maybe if we were to do it like this. Okay, yeah. So we need to do this perk so that it's a 1 by 0 array. If not, it will treat it as a 0 array. Okay, so let's do that. Yeah. Okay, so it worked. So if we shift it to be like 8 or 10, okay, it doesn't learn the shift value because it's sort of the shift is sort of the same. We can actually see the weights for the shift value using this dense 202. So maybe for layer in model.layers, okay, print layer.name. Let's just see what are the layer names there. So if layer dot name is dense 202, I think that's the dense that we want. Is this first dense here? If the name is this, then what we want to do is we want to print out the, okay, so we can get the weights and the bias equals to layer dot get weights. Okay, so let's take a look at the weights. The weights is like this, and we can see the shape of the weights is 2611024. So the weights that correspond to the last node will be the weights of the number 260. So we can see what's the weights for this. Okay, so we can't really see what the statistics are over here. So we can just do like maybe like min of this to see. So it's actually kind of garbage right now. Yeah, I mean there's some weights, but the weights are not really used here. Okay, so maybe the bias term. Let's take a look at the bias. Okay, so it looks like they do have some weights for that last node, but the weights are not exactly. I don't think there's much in these weights. I guess we could see. Yeah, but yeah, it's definitely correct in the 261. Yeah, I guess they did not emphasize that much on that weights. Yeah, so we probably have to see like what the, yeah, so the bias term for the 260 is about 0.008. How come there's a 263? Okay, let's see. Oh, that's for the next few. Okay, the bias is not really nothing to do with that. So maybe we just take a look at weights like 259 to just compare. Yeah, you can see that the mean of the other weights like are kind of larger, I guess. While the weights for that particular one is like slightly low. So it means that probably it has learned to ignore this layer. Okay, great. I mean that's kind of an interesting analysis. Let us just try to make the shift varied now. So we vary the shift. So what we want to do is like this. Okay, so in this shift value equals mp dot random dot rand int. Okay, of course, I mean we could random all 26 of them. Okay, so we can delete away this. Okay, we random up. Okay, maybe I still keep this. Okay, so yeah, we actually there's no need to keep this. We just random the shift value in like this. Okay, and then basically our input will append this random shift value, and then not only that, we could have like maybe shift values. Okay, we can append the shift value that we are using, and we can also print out. So you can see there's some shifts 4, 25, 11, 0, 0, 8. So we have shifted the network by different amounts each time. So hopefully this will be a harder challenge for the network, because the network will then need to learn how to do the particular shifts like this. Yeah. So yeah, we did until 26. Let us see whether the network can learn it. Okay, so as you can see, it's suffering from some. It's not really able to learn here. Once I encoded the shift in, looks like the accuracy has suffered a dip. Yeah, looks like it's not able to correlate that shift to the, yeah, maybe the number for the shift can be like made a little smaller, yeah, so that it can learn better. But surely the network is actually learning. Its accuracy is actually increasing. Yeah, but I don't think it has learned quite well how to deal with the shift. Yeah, so let's take a look at how it does. Okay, so interestingly, it can still learn. It's still learning. Yeah, it's just that now, because the shift value is like kind of different for each of them, the network actually needs to pay more attention to learn the Caesar shift value for the network in order to decode it, which is not natural for neural network, I guess. Neural network, because all the rest of it in the earlier part here is all one hot encoding for all my letters, which is 0 to 1. But then this shift layer is from 0 to 26. So one issue that can already be seen is that the scales are different. Like maybe if I had normalized the shift vector to be between 0 to 1 as well, that can help the network learn better. Okay, so let's just see. So as you can, let's just do a string of 1, 2, 3, 4, 5. Let's do like that. So you can see that just with a string of A's and maybe a shift value of 0, it hasn't learned. Okay, it is confused. The network is confused over how to shift it. So let us see whether we can solve this issue by doing a scaling of my shift variable. So you can see there's a lot of things that oh, okay, I know why I didn't learn anymore. It's not about the scaling. Okay, I did have my shift values here, but silly me forgot to forgot to do this. So it actually should be like this. Okay, I was thinking actually it should be quite easy for a network to learn. I mean, how come it didn't learn? So actually it's because I didn't really like put in the shift values inside. Okay, so to make the problem simple, let's just make the message length as 4 characters, so that we have fewer. Okay, we have fewer of that. Okay, let's see what's wrong now. Okay, so I need to convert to tensor, this one. Okay, so let's see the training now. I've converted my shift, the Caesar shift cipher value into a tensor now, and it's still between 0 to 26. But okay, earlier on I was just giving it a value 6, that's why the network was confused. But now giving it like from value 0 to 25, can it learn? Okay, it looks like it's actually learning pretty decently. Like you see, your accuracy for all of the nodes are like increasing steadily. I think if let it train long enough, this model should converge to the optimal output. So if we were to have enough like samples, the network actually looks like it's learning something. So let us take a look. Okay, so the accuracy is the last 4 here. It's like better than chance guessing, because chance guessing is 1 out of 26, right? We have 26 alphabets, so it is about 60%, which means he has learned something. Let's try for like 4 characters, like A. Okay, so you can see majority of it is learned well. Like 3, oh, 3 learns well. For but not all. Okay, maybe we don't have enough training samples for the rest. Okay, let us see what will happen now if we just do a scaling for my, because right now my shift values here is unscaled. So let's just scale it down by 26. Okay, and let's just take a look at my shift values to just take a look. Okay, so you see we have all scaled down to between 0 to 1. So we can see that the max shift values will be, oh, I didn't know it was going to take this long, but max is 0.9615, which corresponds to 25 divided by 26. Yep. Okay, I mean if want to, we can just divide by 25 as well. Yeah. Maybe let's do that. Hi Commodore. Okay, so you are saying that you don't trust neural networks, right? In other words. Yeah, I mean it is an abstraction, yes, but it's actually based on like a certain mathematical rule, and actually you treat it like you're learning linear regression in a more advanced way, then I guess you could understand how it works. Yeah. But yeah, for now I'm just curious to see whether or not the Caesar cipher scheme with dynamic shift can be deciphered. Okay, regardless whether we understand how it works or not. Okay, can the network learn it? Okay, so that's the main interest of right now. So we can see the shift values. I just want to see what's the maximum shift value. Now I've rescaled it. I think there's also a rescale layer in TensorFlow. Or I could add batch normalization actually. Yeah. So you can do rescaling. Okay. So you could scale like here. Yeah, maybe we could do the scaling inside the model. Yeah. So how do we add the rescale layer? We can just rescaling. Then you put the scale like rescaling 1 divided by 255. Yeah, so that we don't have to do this manually. Let's not do the scaling here. Let's do the scaling over here. Okay, so over here we have input 2. Okay, input 2 equals to rescaling. Of course you can also add a batch normalization, but there's no need to, because we already know the batch normalization is when you don't know like what's the input range is. So rescaling 1 divided by 25. Yeah, let's do a rescaling here. Cannot import rescaling from TensorFlow. Yeah, that's weird. I mean, I typed it correctly, right? Rescaling. Yeah, you're right. Commodore handcrafted is much faster in terms of being able to be deployed, because you know how it works. Yeah, but if you were to do something like if you do something like, if you don't really know what's the rules that are used to get a particular output, like for example something more complex like image identification, like if you were to handcraft the rules for what's a dog, what's a cat, it will be quite disastrous, because there's so many different versions of cats and dogs. So neural networks are great if you have abundant data, and you are able to just let the network learn for itself what is important and what is not. Yeah, so for simpler problems like this kind of thing that I'm doing, like Caesar cipher, indeed handcrafted algorithms are better and in general more reliable. But now the aim is, hold on, the aim is to just see what are the limits for like this kind of neural network based methods, see whether they can learn this kind of things. So Yeah, let's just test. Okay, let's see why my rescaling layer is not there. Okay, for some reason, rescaling is not in TensorFlow layers. Maybe it's called rescale now. Let's take a look. Rescaling layer. Uh, is it still experimental? Okay, so maybe I need to have like x2 over here. Okay, done. So if we have the model, we actually do a rescaling here to divide by 25. Okay, and that will rescale my shift parameter. Okay, and then let's see. Okay, so initially without the rescaling, the accuracy was about 60%. I could get more actually if we actually train longer, but let's see how the scale thing affects the training now. Yeah. I mean, personally, I quite like handcrafting my own algorithms because I feel like you can get more control. Yeah, but I mean, neural networks are amazingly efficient, and yeah, it definitely can be deployed for more stuff. Okay, so surprisingly, after I do my rescale here, it seemed to like worsen the convergence for some reason. So yeah, that's interesting. Okay, I didn't expect that. Okay, so it's like now 22% only compared to previously when I didn't rescale it. So okay, maybe I have to like rerun this because I may have run this thing here, but like, let's just run the whole thing again just to check that everything is okay. Yeah. So the only change was this. Did I scale it? I didn't scale it, right? I didn't scale it here. Oh, okay. I know why. I know why. My shift values. What are my shift values? Okay, let me just run this again just to make sure the shift values are okay. Yeah, the shift values are alright. Okay, somehow after I scale it, the accuracy didn't go up as fast as I expected it to. So yeah, maybe now the issue is not about the scaling. Okay, but like the network may not be able to understand what okay, is understanding the network is understanding what to do with it. Yeah. So one thing now we can do. So just now we got about 60% accuracy without the scaling. Let's see now what accuracy we get. Okay, actually it's kind of worse. Okay, so one way I can think about doing this, okay, is to just maybe okay, so you can see that it kind of didn't really work. Okay, the okay, let's just see if we train it like for a longer period. Like so now this is considered like 15 epochs. You train it for a longer period, see whether the accuracy can hit one. Okay, so this is a little tougher than before because before that the shift was constant. Okay, now the shift is kind of dynamic, so we just want to see whether or not the network can learn this dynamic shift. Like we change the shift value and can respond accordingly. Okay, so it does take a while longer, but it is slowly but surely learning the shift values. You can see that it's now like about 77%, 70. Okay, that's interesting. Okay, that's interesting. I just wonder if, let's say, uh, if we don't give it any examples of a certain shift, can it learn it? just from extrapolation alone? My guess is no, but okay, you can see that the accuracy took a big hit actually. It's no longer as accurate as before. Yeah. So this calls for a fact that if let's say we have another variable that is sort of like a shift, a context variable per se, okay, maybe it is required to change the neural network architecture a bit so that it can learn this better. Okay, so it's about 86%. Okay, let's train it for another 10 epochs and see whether it does any better. So it looks like it can still converge. It looks like it can still converge. It's like 87% now. 89. Okay, I think if you let it train long enough, this may be able to get 100%. Because like after a while, it will learn like all the relations needed in order to get the right output. And then I'm doing the same operator for all of my bits, so it can learn the right function. I'm not too sure actually. Yeah, let's just see whether it converges. Oh, you see, 93%. It's getting better. Yeah, so maybe it is harder for the network to learn the shift operator because it is like sort of affecting the mapping. And yeah, in order to do different differential mapping, we need some sort of like masking perhaps. So we can try to implement some form of masking. All right. Okay, I mean it is getting quite accurate, but not fully accurate. And the validation is like slightly lower than the training. Okay, so it's about 90%. We can see. Okay, so if like A and we shift it like that, not bad, not bad. How about A. Okay, so it can shift pretty well already. It's not too bad. It's just not perfect. The accuracy is like 90%. Okay, let's see what we can do to make the model perform better. So this rescaling apparently didn't really help. So I'm just gonna take it out. Okay, another way that could help is I'm pretty sure that if we were to do some form of like one hot encoding for this, okay, I'm pretty sure this would help. Okay, why? Because it's easier for the model to learn from ones and zeros than it is to learn from like a variable data. So one way to like change this model to make it work well is to use one hot encoding. But the problem if I use one hot encoding is that I will not be able to test what I want to test. Okay, I want to be able to like give it like only certain examples of the scaling and then like see if they can extrapolate to the right amount. So maybe what I can do is yeah, maybe I just don't change this. Okay, we have x input 2 like that. Okay, maybe what I want to do is maybe we just give it another dense layer. Okay, and then we just see whether this works better. So it's a double dense layer. It's like more structure, I guess, more capacity for it to learn. Let's just see whether it learns. Okay, so yeah, it did improve a little bit of the performance, although now it's getting harder because there's oh not bad. Yeah, so it actually a deeper network improved the convergence speed. Yeah, not bad. It's not bad actually. It's improving pretty well. Yeah, so I think this model has the potential to learn. I mean, other ways that you can tweak it is to change the optimizer and see whether it works. Okay, so this network looks like it's doing well. Oh, it's doing great actually with this. Okay, which means that we can implement our next challenge. Okay, which is to do something even harder, an encryption scheme that is even harder. Okay, so it's about 91%. It's not too bad actually. It's not too bad. Okay, now it's about 96% already. So it's amazing how much one more extra layer help it to converge. It's like a deeper network. Okay, not too bad. It's about 93%. Okay, about 93%, and you can see that indeed it. I guess there's some cases of shift values that okay. So maybe we just okay. So we can do a value counts for this. We can see that the random number generator actually did generate quite evenly for all the shift values. Yeah, so I think it's fine. Yeah, it's not about the missing data or what, but maybe we can just do like input shift values. Oh, what did I call that variable? Train input shift. So the train input shift is quite similar. Train input shift, val input shift also around quite some test input shift. Yeah, so I don't think it's a problem about the variation or the distribution of the data. The issue is perhaps like the model may not be like deep enough to contain all this. Okay, so that is more or less this model. Okay, I want to do something even more crazy. Okay, so now we have a dynamic shift of 0 to 26, right? So what happens if we were to shift it like by 27? So I mean, this model obviously hasn't learned this, but let's say we shift by 26. What if we shift by 27? So actually, the model still treats it the same way. So you can see that based on this shift here, it's not changing anything because it hasn't learned to, like, for example, do the modulo function to do this. So you can see that it's not well defined outside of the shift values, but within the shift values, it's doing a great job. Okay, so right now, maybe we can do something even harder. Okay, let's just copy this code and do something different. So let's see. Just gonna copy this whole thing. Or can I just like do a okay? Where did I put my code? Decrypt. So let's duplicate this and maybe we call it function cipher. Okay, so we are done playing with decrypt. Okay, so in this function cipher, okay, the scheme will be converts alphabet to 0 to 25, apply function fx to the to a number x between, apply a function fx, then take modulo 26, apply a function fx that maps, okay, from the real number, that maps from natural number to natural number, and get back another alphabet. So there's no more dynamic shift, it's just a function. Maybe the function can have another parameter, has a conditioning term s. Yeah. So similar in construct, just that instead of doing the Caesar cipher now, we just apply an arbitrary function. Okay, so this is a significantly harder problem. Okay, because we do not just want to do a certain shift. Okay, I mean it is still a one-to-one mapping actually, so I'm pretty sure the network can still solve it. Okay, so let's try. So instead of having a shift like this, okay, now we want to do is we want to get our x. Okay, x equals to alphabet shift dot find car. Okay, this will be our x. And then what we want to do is define function, and then the function has a x and a s. Okay, so what we want to do is like maybe we can do this is an arbitrary function to shift the data. Okay, so this function will still be quite easy. So this function will be maybe like return x times x minus s, something like that. Yeah. Okay, and then maybe what we'll do is out plus equals to x modulo 26. Yeah, maybe we do the modulo 26 here. Okay, so I'm just curious what will happen if we do like a minus 5 modulo 26, because we do not want it to. Okay, so it's good. Python helps us do it automatically. Okay, so it should be fine. So regardless of whatever I do here, so like maybe I will get something. So like 5, I will get something. Yeah, so the function may not be a one-to-one mapping. The function may be an even more complicated mapping. So it's the mapping function. Okay, so the way our input is defined has changed. Okay, we do have a shift value. Okay, but the shift value now is not just a Caesar cipher anymore. It is a function. Okay, so let's see. So we have like this function AAWN. Okay, it doesn't really make sense to us. Okay, but it's mapped based on this function. Yeah, so I guess we can just see like a function 0. Okay, let's put function I0. Okay, we just print out this array here. I maybe S for S in range 26. Yeah, so we can get a few of like what happened to it. So in this case, it is like, oh, why did I put I? Okay, so it should be like 0 will be mapped to 25, 24. So it maps quite well. 1 will be mapped, oh, actually also quite well mapped. Oh, but this because of the shift S that is constant. So let's say if I were to put this as a character instead, and then I put a shift 0. So based on the character, you can see that as we look through the characters here, the mapping might be constant for some characters also. So if we do a character with shift 1, so this is just a shifting. So it's not a one-to-one mapping anymore. Okay, you can have certain characters map back to the same number again. See, like this. So it is like slightly more difficult, I guess, yeah, because you have more mappings. But let's see whether the neural network can handle it. I don't have to change all this. Oh, TensorFlow is not imported, so let's do it here. Okay, so let's see whether if we replace it by a function, whether the neural network can still work. All right, out of memory. Okay, that means I need to shut down my kernels. Okay, I don't shut down this function cipher because I'm still doing it. Let's see. Okay, kernel, restart and run ourselves. Okay, so it's learning something. It's learning the function. So it's not a direct mapping. It's a functional mapping, and it's still learning pretty well. with just the linear layer. Okay, because it's still a one-to-one mapping. I mean, as much as the conditioning can like change the function, it's still a one-to-one mapping. Okay, I'm pretty sure actually if I were to like change the condition, the like you see your S over here is it's a linear shift. Okay, but because of the modulo function, if I were to change this S, okay, it may not work for all ranges because it doesn't know how to do the modulo. Neural networks cannot do modulo very well, as what I've found out. Okay, so let's see what happens now. It's not bad actually. It's not bad. It's getting about 0.8284. Yeah, it's actually doing pretty well for. But to be honest, from the network's point of view, because we are giving it all the inputs, from the network's point of view, it is still doing like an interpolation. It already knows what to map to. Okay, because it has been given that sample before. Yeah, I mean it's not too bad. Yeah, it's about 90% accuracy, and you can see that like if we were to do this, like a, you can see that it actually maps pretty well. Oh, see, there's some error already. So by for certain shift values, certain certain parts learn better than others. Yeah. So I mean, if the cipher was like that, right? Actually, it would make more sense. Okay, if this dense part here, okay, like this thing here, if we apply this same function to multiple, so instead of having it separate, like you can actually have it share weights. Okay, so then it will learn super fast. Okay, let me just demonstrate this. Okay, so let's say map function. I'm just gonna change the structure of the network a bit, so we can just do this map layer equals this, so we can apply the same function many times. Okay, so it shares the weights like that. Yeah, so we only have 126 here, which will be trained on. So basically how this layer works, the the layer would take in from the previous input, but then how it interprets the input will always be the same. Okay, but actually that may not be true because we want different alphabets coming out from different inputs. mm, and the input is the same, so yeah, no, let's not do this. I don't think this will work. Yeah, because we want different outputs coming out from the layers. Okay, but what could be done is that we could actually, yeah, I think this cannot be changed. Okay, so this is a good enough model. Let's up the difficulty for the network. Okay, what if now my function is different for each of the alphabets? So I do a different function for the alphabets, and the function can be based on like uh, previous data as well. So like maybe the function is based on all the x's. So we do have four different functions for it. So we let's have a list of x. Okay, so we can have a function like uh, a b c d equals to x0, x1. Okay, actually let's not do something like that. Maybe we can just do like x0. Okay, so we do need to define like four different functions. So we can define like that, like that. So instead of doing this, what we can do is we can let it depend on like all the data. So it makes it even harder. Okay, so maybe like this. So we make our function like work for it. One, two, three. Okay, I'm not even doing a symmetric function here. I'm just like, okay, just maybe something like this. And maybe the last one just depends on x0. Okay, and the shift, you can even do it like that. Plus, minus, plus, times. Let's make the model work for it. Let's make the equation so hard that the model will have problems learning it. Okay, so you have to see this now. So we have a function here that returns four of them. So what we want to do is we want to apply this to the character. So we have x like that. Okay, so we do have indexes equals to this index.append x. Then we do a alphabet. We basically do a okay. Then we also can do another layer. So we do have the indexes, and then we can just put this here. There are four indexes. New indexes will be alphabet shift. Actually, will be equals to function indexes s. Okay, so we have a very weird and arbitrary function here. New indexes equals to this. Okay, and then we will just do like out.append. Yeah, out.append new indexes I from the alphabet shift. Oh, so this should be a plus equals to because it's a string. So yeah, now we have come up with some arbitrary complicated function here that even I don't know how to solve. Okay, it's just some weird thing that I just, so it's just like multiply, plus, minus, whatever. Yeah, this last one is especially hard. It multiplies with the shift operator somehow. So let's see whether the network can solve it. So we see, you can see that this is the desired output for this text. Okay, so let us see whether this works. Convert this. Nothing needs to change for the network. Okay, so now let's train it. Okay, it is going to be difficult because it relies on a lot of interactions with the previous variables, including some multiplication and so on. So let's see how good the network can be in learning this. Oh, surprisingly, not bad actually. Given the complexity of the functions, it's actually learning pretty well. Yeah, and somewhat the output actually depends a lot on like on the interaction variables between like all of these indexes. So it is pretty amazing that they actually can work so well. I expected worse actually, yeah, because this is a super tough problem that a neural network should have difficulties solving. A lot of intricate things that needs to be done, and yeah, that is actually going to be the focus of the next stream. Yeah, that will try to make the network perform better at some arbitrary function that involves a lot of like some polynomial. Yep, you can see that it's about 60%. I honestly don't think it will rise even more. Let's train it for another time epochs and see what happens. Let's train it for another 10 epochs and see whether it improves. So it's about Oh, so there's only one accuracy is about 60%. That's the last one that does with this shift operator. Okay. The rest at the front here, you can see that the accuracy is like quite horrible. It's like 0.04, 0.06, which is expected because I did it this kind of terms. So these kind of terms can't really be found by the network, but this can. Okay, because this is ultimately just based on the shift operator, and you just adjust accordingly. Okay, let's just train the network again for another 10 epochs, and we see whether there's any improvement. Okay, we give it some chance. Okay, we make sure that it learns the basic that it can learn. Okay, it looks like it's able to classify a bit more. It's learning better. Okay, but let's see how well this very native structure that uses like a 512 dense layer like that can work. Okay, then maybe the next time around we'll try to implement more complex structures like maybe REST nets, that kind of stuff that perhaps can help to solve this problem. Yeah, so we see whether we can do it. Okay, although I think for this particular case, REST nets, even REST nets may be difficult because of the way this function is defined over here. So yeah, let's see whether we can solve it with a more complicated model. Yeah, so this is a problem. Okay, with like current neural networks. I think current neural networks cannot do like multiplication modulo very well. And if your use case relies on it, most of the time what I see people do is they just add in the hard-coded or handcrafted equation inside the network itself. Yeah, but neural networks can do stuff like see image processing really well. I think functions wise, still lack a lot of room for I mean, still have a lot of room for improvement because the neural network itself is just simply a summation of weights multiplied by the inputs. Yeah, it need not exactly be that great for doing multiplication between variables like what I did above here. Like if your function requires you to multiply indexes like that, good luck. Yeah, I'm not even sure whether ResNets can solve this. Oh, we will try that in the next stream. Try to use ResNets, try to solve this. ResNets is called residual networks, by the way, which are supposed to be one of the better ones to actually help to encode a very arbitrary data, something like okay, so it is actually like this, a lot of skip connections. But the main idea is here actually. Instead of like going through the layers like that, we actually have an identity function that goes through, and then we add like a batch normalization block here in order to basically prevent the gradients from like vanishing or exploding. Okay, so that's ResNet. You can try ResNet next time because I've got to go. But you can see that it's kind of crappy. The performance is like for the last digit, for the last character, it decodes it quite well, like 57% of the time. But for the first three, it's abysmal. It's like 0.06. So if let's say we have like 1 divided by 26, right? That's about 0.04. So it performs like this one performs about the same as random guessing. And this two over here performs around the same as twice, maybe it's like slightly more accurate than random guessing by a little bit. Okay, so let's see. So let's okay, this one we don't need this. Let's delete this. So we have this, and then we can just print. Maybe here is like model prediction is this, and then prints actual string get output string plus the shift value. Okay, so we need to implement this actual string function. Let's just do it. So we do have a shift over here right now. So actually the actual string function is just this shift function. So we can just do this shift function. Okay, so the model prediction is like NMVA, actual is UBRA. Okay, that's fine. So like over here, it predicts wrongly all the time. So yeah, if we make the cipher a little more complicated, Okay, it's not good. Yeah. Okay, so like we try to tackle this issue the next stream. We try to tackle solving this kind of arbitrary functions in a nice manner for like Cipher. Okay, because actually a lot of ciphers use this kind of modulo, use like SHA encryption, that kind that involves like also a random keypad. Okay, but that I don't expect the model to learn because the random keypad is supposed to be for encryption, and like those one-time keypads, you probably can't use a neural network to solve it because it's randomly generated. Yeah, and it's provable that it's already encrypted quite well. Yeah, this kind of deterministic functions like this, I think it can be solved. I think it can be solved. But right now, we are not really modeling all this, right? Okay, anyway, I got to go, and see you all next time. Okay, bye.